So great. So, hello everybody. Thanks for joining today again to this Quantum Spain seminar series. Today we have the pleasure to have the collaboration of Richard Allen, who's he's a very young speaker. Despite his youth, he has a extremely nice record of papers with very high scorings. Richard has Nature, Science, and many papers, and with very high number of citations. Richard is graduate. He graduated in Harvard in 2022, and he's now a PhD student at MIT. And his work is centered about quantum metrology and sensing, especially in connections to algorithms and complexity, as well as the use of chaotic quantum dynamics for fundamental information processing tasks on modern quantum devices. So Richard today is going to report on his last paper, which I think is very exciting because here in this series, as I was telling him, we mainly focus on quantum computing, but his paper is going to bring us a little bit outside this comfort zone and bring us to the field of sensing. So the title of it is Quantum Computing and Enhanced Sensing. So Richard, the ground is yours, and so we'll have questions at the end after about 50 minutes. Yes. So thanks.
Perfect. Thank you very much for the generous introduction and for the invitation to speak. And thank you to all of the attendees for your interest. I hope that this can be engaging. So I will go ahead and share my screen. Okay. Let's see. Can everyone see my slides?
Yes, we can see it.
Great. Good. So as we said, today I'll be speaking to you about our recent work on quantum computing and enhanced sensing. My name is Richard. I'm a PhD student at MIT. Before we begin, I'd like to take a moment to acknowledge some of my co-authors. So in particular, Francisco Machado. He's an ITEM fellow at Harvard with whom I worked very closely on this work. Also, Isaac Chuang at MIT, Robert Fong at Caltech and Google, and my advisor, Sumon Choi at MIT. So I think we can all agree that right now we're living through a very exciting time in quantum science with rapid progress in really all aspects of the experimental design of our many-body quantum platforms. So in particular, high-fidelity operations, the advent of logical qubits and circuits, and also the development of large coherent arrays of many, many qubits. And as we witness these exciting developments, I think it's more important now than ever to ask ourselves the question, what should we do with our quantum devices? And in this talk, we'll perhaps attack one aspect of this question. So one thing that we can do with our quantum devices is quantum sensing. So quantum sensing is a very promising application of quantum technology. And at this point, quantum sensing is really responsible for humanity's most advanced measurements of many things, many physical phenomena, ranging from gravitational waves to time through the design of atomic clocks, to fundamental physics and the estimation of parameters in particle physics, to magnetic fields and many, many more physical phenomena. And anything that we can do to advance the tide of quantum sensing is really, that's progress towards better science in general, not just better quantum science. At this point, I'd like to walk you all through, because this is maybe a more computation-based group, to walk you through sort of the standard paradigm in quantum sensing, or what typically people mean by quantum enhancement in sensing. So the simplest and in some sense most prototypical sensing problem is the detection of a time-independent magnetic field. So in this setting, you have maybe just a single spin, which couples to some unknown magnetic field in some known basis. So the field is of strength B, and the goal is to really estimate B. And if you have a single sensor, a single quantum mechanical particle, there's a simple protocol for doing this. So you prepare your sensor in a state, for instance, like the plus state, which is orthogonal to the axis of the magnetic field. You let it time evolve, and then you perform some measurement. And you use this measurement, the classical statistics that come from this measurement, to estimate the strength of the magnetic field. And the sort of standard figure of merit in quantum sensing is the sensitivity, or the minimum detectable signal strength. And the minimum signal strength which you can detect, it scales like 1/t, which is the sensing time. And then the reason for that is you need this angle of phase accumulation to be order 1 in order to detect the signal. So you need b times t to be order 1. So this 1/t scaling, this is really like the fundamental limit for detecting time-independent magnetic fields if you have a single sensor. But that's not all you can do in quantum sensing. One thing you can ask is what you can do with many sensors. Well, one thing you can do with many sensors is just take the single sensor protocol and run it many times independently. So you can let each of your sensors evolve independently under the magnetic field, measure them one by one, and then use the measurement counts to estimate the field. And if you do that, your sensitivity improves by a factor of square root n, where n is the number of sensors. And the reason for that is just classical statistics. If you have n independent measurements, you get a root n improvement in the sensitivity. And one of the sort of key or prototypical results in quantum sensing is that this is not the best. This is not the fundamental limit for sensitivity to time-independent fields. And in fact, this is known as the standard quantum limit, but it's not the fundamental limit. And in fact, if you have many sensors and you prepare them in some entangled state, you can use this entangled resource state to sense better, more efficiently, and to detect weaker fields. And the way that works is if you prepare your sensors in some particular resource state, then the state of the entangled sensors behaves like one large coherent spin with a collectively enhanced coupling to the magnetic field, collectively enhanced by a factor of n. And the state of this collectively enhanced spin evolves in some sort of larger effective Bloch sphere. And as a result, the sensitivity improves by a factor of root n over the standard quantum limit, or factor of n over the single sensor limit. And this is called the Heisenberg limit for sensitivity. And this really is the fundamental limit for detecting time-independent fields using n quantum sensors. And this is all very good, and it's led to many experimental and theoretical works for achieving the Heisenberg limit in quantum sensing. But in this work, we are not going to be talking about sensing time-independent fields. Instead, we'll be asking the question, are there other qualitatively different sources of enhancement in quantum sensing? So different than just collective enhancement due to entangled resource states. Okay, and in particular, we're going to consider a new quantum sensing paradigm, which we call quantum computing enhanced sensing. And maybe to set up this paradigm, let me contrast it with this typical or conventional setting in quantum sensing that I've just described. So conventionally in quantum sensing, while it might be possible to prepare some entangled resource state as an input, subsequently, this resource state is controlled sort of classically in the sense that you apply a sequence of pre-programmed quantum gates, which are often single qubits, and you can imagine them as being just sort of controlled by some classical computer. Let's contrast that with a different setting, which we call quantum computing enhanced sensing, where instead of classically controlled gates, you can apply quantum controlled gates. What do I mean by that? Well, I mean entangling gates, which act between some quantum computer, some small quantum computer, and your sensor. So you can prepare the sensors in an entangled state, but you can also apply entangling gates or run quantum algorithms throughout the sensing step. And the key question in this new paradigm is whether or not quantum computing can be leveraged to improve quantum sensing. So is this new setting, is it fundamentally different than the conventional setting? What new problems can we solve and how efficiently can we solve them? Okay, so this leads us to outline for today's talk. So as I said, sort of for time-independent sensing, the Heisenberg limit is really like the fundamental limit. So we'll need to consider a different but still physically motivated sensing problem, and that's AC sensing. So let me first introduce the problem of AC sensing. AC sensing is fundamentally, it's the problem of detecting weak oscillating signals as efficiently as possible. So these are signals which are not time independent, but they're sort of the next simplest thing, which is just an oscillating signal, like a sinusoidal signal. And so what would the typical sort of workflow for an AC sensing experiment look like? Well, there would be some signal source for this AC field. That source might be axionic dark matter, for instance, or some sort of spectroscopic signal, or even gravitational waves. These signals would then be intercepted by some corresponding quantum detector. There would be some amount of quantum processing, perhaps by a quantum computer in our new setting. And then finally, the output of your protocol, your algorithm, should be some binary answer, yes or no. Is there a signal or is there not? And that's what we call detection. That was sort of a schematic description of AC sensing, but at the end of the day, our goal is to prove things and to be rigorous, but still physical. And so let's be a little bit more formal about this AC sensing problem. So formally, we assume that there's some signal, which is oscillating in the following sense. So it's B cosine omega t plus phi, where these parameters B, omega, and phi are not known. And we assume that the signal couples to your sensors in some known way. And for simplicity, let's just say that it couples to n sensors in the Z basis. That's sort of an arbitrary choice. And as I said, these parameters B, omega, and phi are not known in sensing. But I mean, they're not completely unknown because that problem would take an arbitrary amount of time to solve. But rather, we know that if the signal exists, then the field strength B is going to be larger than some minimum B min. And the frequency, it's not arbitrary, but it lies within some known interval, delta omega. The phase, on the other hand, because it's sort of an arbitrary parameter, we'll just assume it's completely unknown. It could be any value. And these parameters, B min and delta omega, they sort of determine the difficulty of the problem. We can think of these as inputs to a particular instance of this AC sensing problem. And so we can formally define an AC sensing problem in the following way. It's to decide whether or not an AC signal exists with B larger than some minimum B min and omega within some specified bandwidth delta omega. And the goal is to do this in the minimum possible sensing time, which we'll call tau. And so this is our physical resource, is the amount of clock time that we need to sense the field for. And we want to solve this problem as efficiently as possible. That means minimizing that time. And I want to emphasize here that this AC sensing problem, I mean, although we've framed it in a sort of precise and mathematical way, it really is a practically useful problem. I highlighted on the previous slide that many like natural problems in physical science sort of look like AC sensing. So dark matter detection, various problems in spectroscopy, gravitational wave detection even, they all resemble an AC detection problem. And moreover, this AC sensing problem is conceptually important because it's sort of the minimal example beyond time-independent sensing. And so if you're interested in understanding the sort of difficulty or complexity or fundamental limits for time-dependent learning or time-dependent sensing, then this AC sensing problem is sort of an important first problem to look at. Understanding the fundamental limits and optimal protocols for AC sensing is worthwhile for this reason. Okay, so before describing our approach, let me just briefly review existing strategies for AC sensing. Because as I emphasized, this is a real physical problem, which people in the lab are trying to solve, experimentalists are trying to solve. So how do they solve this problem? Before we talk about the general problem of AC sensing, as I described it, let's imagine that you actually know the frequency omega. So what if you know omega? How do you detect the signal then? Well, in this case, there's actually a rather simple protocol which you can perform, and it's often called the CPMG sequence. CPMG those are the initials of the protocol's inventors. And the way CPMG sequence works is if you know the frequency of the field, then you apply pi pulses or X gates resonant with the frequency of the signal you're trying to detect. And when you do this, the effective signal in the toggling frame is everywhere non-negative. So it's a sort of positive signal. And as a consequence, you can perform the same time-independent sensing strategy that we described on the first slide, and you get just coherent phase accumulation. So it's possible to detect the signals by applying resonant pi pulses. And good. So that is what you would do if you knew the frequency omega. And we can ask, what's the performance of this protocol, this simple protocol? Well, the sensitivity of the protocol, the minimum detectable signal strength, still scales like 1/t, same as in time-independent sensing. And we're not sensitive just to signals at frequency omega, but rather to signals with a frequency that lies in some bandwidth, which is Fourier limited. It scales like 1/t, the sensing time. And so if you were to plot the response of the sensor as a function of frequency, what you see is that it's peaked at omega, but there's some width, which is of order 1/t. So you can detect signals within 1 over t of this target frequency of your CPMG sequence. Okay, so that is how you would detect signals at a known frequency. If you don't know omega, then we can use this analysis on the previous slide to design a sensing protocol for this general AC sensing problem. And the way that you do that is you take your full bandwidth, delta omega, and you just divide it up into a number of frequency bins, which are of width little delta omega, which is the bandwidth of an individual sensing step. And then you just, for every one of these bins, you're going to apply a different CPMG sequence at a different target frequency so that you're sensitive for each bin to the frequencies in that bin. And you just scan your target frequency across the bandwidth to detect the signal. And so the key takeaway here is that by sequentially searching across multiple frequency bins, we can solve this AC sensing problem. And this, I mean, I've described a sort of maybe overly theoretical version of it, but this is basically how in the lab right now, experimental groups are searching for axionic dark matter or other AC signals by performing a linear scan across frequencies. Okay, so what's the performance of this strategy? Well, we're just going to extend our analysis for the single frequency case. Again, the sensitivity of each step is 1 over t, so is the bandwidth. But now there's many frequency bins. The number of frequency bins is the overall bandwidth divided by the width of each CPMG sequence's bandwidth. And then if you combine these parameters to figure out the overall sensing time, well, it's the number of frequency bins, it's the number of iterations that you perform, times the duration of each iteration, t. And by combining the scaling relations above, we find that the overall duration of the protocol it's linear in the bandwidth, and it's inverse quadratic in Bmin. And that's the amount of time that this protocol takes. This was for a single sensor. If we allow multiple sensors, then we can prepare them in some entangled initial state, same as in time-independent sensing, and we get a corresponding improvement in the sensitivity. And the overall sensing time for this protocol with an entangled initial state has the following scaling. Okay, so I've described the results in one picture where you have Bmin and delta omega fixed, and the goal is to minimize the sensing time. There's a sort of dual picture where you imagine that the total sensing time available to you it's some resource which is fixed, and you want to understand which signals are detectable in a fixed total time. And that leads to the following plot. So this plot you should think of as telling you which signals are detectable for a fixed total time tau. And the goal is to sort of unlock more of this parameter space. So more efficient protocols are able to detect weaker signals over a larger bandwidth in the same total time. And what this plot shows is that by preparing an entangled initial state, you do access like a larger fraction of this parameter space, but the scaling of this boundary, which is like the slope of the line, that doesn't change. So this is the kind of improvement that you get from an entangled initial state. Okay, so the discussion so far has been a priori not very connected to our motivating question, which was, can quantum computing be leveraged to improve quantum sensing? So let's return to that question and answer it. And this takes us to our first main result, which is that there is in fact a quantum computing enhanced sensing algorithm which solves the sensing problem in the following total time. So it's 1 over ns Bmin square root delta omega over ns Bmin. And if we compare this with the previous result, we see that the improvement we get is as a square root of this delta omega over ns Bmin, which is sort of the number of frequency bits. So we get a square root improvement in the number of frequency bits, which is very large because we're interested in the regime where the bandwidth is very large and we're detecting very weak signals. So delta omega over Bmin is a very large number. We call this algorithm quantum search sensing for reasons that will hopefully become clear. And sort of one technical point about this result, this O tilde, this is standard notation in sort of algorithms or complexity. It means that this result neglects logarithmic factors in delta omega over Bmin. So this is true up to log factors. Okay, so there exists a protocol which has this performance. Our second main result is that this protocol is optimal. Quantum search sensing is really like the best, basically as good as you can do, because any quantum sensing protocol which solves the sensing problem has to take a time which scales in the same way. We call this lower bound the Grover-Heisenberg limit. Again, hopefully this will be clear soon, the terminology. And again, the take-home message is that our QSS algorithm is optimal up to these polylogarithmic factors. Okay, so how does this modify our diagram of which signals are detectable? Well, we sort of unlocked a new region of parameter space by using the QSS algorithms. There are new signals which can be detected in a fixed total time. And again, sort of the way that you should interpret this plot is like as a function of number of graduate student lifetimes, like what region of the axionic dark matter parameter space can be probed. So if you have access to a quantum computer, which is some new resource, then in fact you can take fewer grad student lifetimes to detect weaker AC signals across a larger bandwidth. And moreover, because of our second result, the scaling of QSS is really as good as you can get. And outside, all other signals are in fact impossible to detect. So these two results, basically, they sort of settle the question of which AC signals are detectable and which are not. Okay, so that sort of brings us to the end of the results and motivation. I'll now describe the actual quantum search sensing algorithm, unless there are some questions. Okay, if not, I'll move on to describe the algorithm. Okay, so before introducing the algorithm, let's recall the existing strategy that I just described. The main takeaway there was that by sequentially searching across many frequency bins, we can solve the sensing problem. And the keyword here is searching. That's what we want to hone in on. And the reason is, as many of you probably know, quantum computers are sort of good at searching. There is a provable speed up for search, which is achieved by Grover's algorithm. And we want to take advantage of this speed up to improve quantum sensing. So the strategy is going to be, if we can map our sensing problem to a corresponding computational problem, then we can leverage existing quantum algorithms to sense faster. There will be a number of complications, and that'll be sort of the next section of the talk to discuss these. Okay, but before we get into those complications, let me describe what a search problem is, just very quickly review. So a search problem, unstructured search problem, you can view in the following toy way. Given n identical, otherwise indistinguishable boxes, we want to find one special or marked box. And the way that you'd solve this problem, classically, there's sort of nothing you can do but randomly query individual boxes. So you just search them one by one until you find the special marked box, which will denote K star. And if there are n total boxes, then classically, this is just going to take a linear number of queries, order n queries. And the extremely remarkable and surprising fact is that if you have a quantum computer to do this search, then in fact, you can find the marked box using just square root n queries. And the algorithm which achieves this is called Grover's search algorithm, which many of you may know. But we should slow down and be careful with the way that we answer this question. We should, in particular, ask what it really means to query quantumly. So, like, what does it mean to check this box quantumly? Okay, so the quantum setup is you have these n boxes. They're going to be encoded as different states of some quantum computer. So you have a quantum computer on log n qubits. Each state of that quantum computer corresponds to a particular box. And quantum queries, what we mean by a quantum query is that you have available to you a quantum oracle, which acts in the following way. You feed the quantum oracle a particular state of the quantum computer, state K. And if K is equal to K star, so that's the marked bin, then you want to mark the state with a -1 phase. Otherwise, you do nothing. So the quantum oracle should apply a phase flip of -1 to the marked state and act otherwise as identity. And then it acts in superposition. And by square root speed up, what we mean is that the number of queries that you need to this quantum oracle is just square root n. Okay, so in order to achieve this square root speed up for search, we needed a quantum oracle. And so in order to leverage the speed up for sensing, we're going to need to design some sort of sensing oracle. So something which acts like the Grover quantum oracle. And so the setup here, we don't have boxes, which we're trying to query. Instead, we have frequency bins. And so we have our bandwidth, we divide it into frequency bins, and then each of these bins is going to be encoded as a state in the quantum computer. The total number of states again, will scale like the bandwidth divided by the sensitivity, delta omega over NSB min. These different states will be states of some quantum computer. And our goal is to design what we call a sensing oracle, which should act in the following way. First of all, the sensing oracle no longer acts just on the quantum computer. It has to act jointly on the quantum computer and the sensor, because the role of the sensor in this picture is sort of to transduce the external signal from nature to the quantum computer. And then we'll run Grover's algorithm on the quantum computer. So it should act jointly on the two. On the quantum computer, it should mark the marked bin with a -1 phase. So the marked bin is the bin which contains the actual signal frequency. So it should apply a -1 phase if the signal frequency is in bin decay. Otherwise, it should act as a density. And moreover, the state of the sensor should be, the sensor should return to its same initial state. And in particular, it should be unentangled from the quantum computer at the end of the evolution. And the reason is we're going to need to use the sensing oracle multiple times in order to run Grover's algorithm. And so we can't have the state of the sensor depend on the unknown frequency or other unknown parameters. And if we can design a sensing oracle which works in this way, then sort of we're golden. If we engineer the sensing oracle, we can then just run Grover's algorithm to solve the AC sensing problem with a square root n speed up. And this square root delta omega over NSB min, well, that's exactly the speed up which we saw in our main results on the early slides. Okay, so now the goal is just to engineer the sensing oracle. And that, as it turns out, is a little bit complicated because of some fundamental differences between the way that the sensing oracle should act and the way that regular quantum sensing protocol should act. So I'll now describe some of those key features of the sensing oracle which differentiate it from regular quantum sensing protocols. The first key feature is that our sensing oracle needs to enable sensing in superposition. So what do I mean by that? Well, let's take a look back at the CPMG sequence, which remember was this single cube, or this single sensor protocol for detecting oscillating fields. In the CPMG sequence, you apply pi pulses at some frequency, and you're sensitive to signals which are resonant with your pi pulses. So you get a frequency response which is peaked at just one frequency. To contrast that with what the sensing oracle needs to do, the sensing oracle should instead have a conditional response. So the response of the sensor should be different depending on the state of the quantum computer. So if the quantum computer is in the 0 state, then there should be response at some frequency omega 0. If it's in the 1 state, you should have response at omega 1, so on and so forth. And this kind of behavior, I'll convince you, is actually not hard to engineer. This is not the difficult part of engineering the sensing oracle. Because one very simple thing that you could do in order to engineer this response is just apply a CPMG sequence conditional on the state of the quantum computer. So if the quantum computer is in the 0 state, then we apply a CPMG sequence at 1 resonant frequency. If it's in the 1 state, we apply it at a different resonant frequency, and so on. And this engineers this conditional response. So sensing in superposition is not hard. The sort of trickier feature of the sensing oracle is that it acts in a digital way. So what do I mean by that? Let me illustrate it with an example. So let's again look at the CPMG sequence as a motivation. So recall that the way the CPMG sequence worked is in the toggling frame, it maps to an effective signal which is everywhere non-negative. And then you can detect it just using the time-independent sensing protocol. But this picture assumes a particular phase relationship between your pulse sequence, the pi pulses, and the signal. And if that phase relationship is not satisfied, if the signal is phase shifted, then the effective signal is in fact, it still averages to 0. And so you actually can't detect this signal using the time-independent sensing protocol. And this is a problem in our setting because this phase phi is not known. Now, there are sort of simpler ways of resolving this phase problem in regular CPMG sensing. But my goal is not really to point to this specific problem, but to point out a general feature of conventional quantum sensing protocols, which contrasts with our sensing oracle. So conventionally in quantum sensing, the response of your sensor depends in a continuous way on the unknown parameters, for instance, b and phi. And there's very good reason for that. In sensing, typically the goal is to estimate these parameters, to estimate small fluctuations in the parameters. So you want the response of the sensor to be continuously varying with these continuously varying parameters. By contrast, our sensing oracle should act in a digital way. So for a continuous range of these unknown parameters, for a continuous range of values of this time-dependent signal, the response of the sensor should be identical. So we need a discrete response despite the fact that we have continuously varying parameters. And I want to emphasize that this digitization, which our sensing oracle must accomplish, it's really like a crucial part of interfacing quantum sensors with quantum computers, I think. It's not some quirk of our protocol that we achieve this digitization, but really, if you want to interface digital quantum computers with continuous quantum sensors, digitization is, I think, a key component of that relationship. Okay, so enough talk and motivation. Let me actually describe to you how we engineer the sensing oracle in a way which is digital and which senses in superposition. And there'll be three key ingredients. The first is phase agnostic or phase independent sensing. The second is sensing in superposition. And the third is nonlinear signal processing. Maybe I'll pause for just a second if there's a question on this motivation before we get into a few of these technical details. Okay, if not, let's move on. So the first ingredient, as I said, is phase agnostic sensing. And these next couple of slides will be definitely the most mathematical or technical because I want to be honest with you about how the algorithm works. But if something doesn't make sense, please interrupt. So our goal ultimately is to engineer the sensing oracle, which applies a -1 phase flip to the mark state of the quantum computer. As an intermediate goal, let's try and engineer something that we call an elementary sensing unit, which is also a controlled rotation of the sensor, but it's not by it's not a phase flip, but it's a controlled rotation by some other unknown angle. But the angle is independent of the phase phi of the magnetic field. So this is what we call phase agnostic sensing. It's the response of the sensor is independent of the phase of the input magnetic field. So this will resolve the problem that I illustrated on the previous slide. And the key idea to engineer phase agnostic sensing is actually AC stark shift, which is a phenomenon in AMO physics, quantum optics. And the way AC stark shift works is, okay, well, this is our original picture. So we have a sensor with levels 0 and 1. And the original Hamiltonian is interaction with a magnetic field, B cosine omega t plus phi. Here I've depicted it as if it's in the x basis, whereas before it was in the z. This is, not important. The two are related by Hadamard. So you could always engineer one from the other. Let's imagine that we add a time-independent control field at some strength omega 0, which we can control, the experimentalist. If you look at this Hamiltonian in the rotating frame which rotates at frequency omega, then you get a time-independent effective Hamiltonian, which looks like this. So it's time-independent, and it corresponds to just Larmor precession about some fixed axis, which depends on phi. But the key feature of this effective Hamiltonian is that its eigenvalues are phase independent. So even though the axis of rotation depends on phi, the eigenvalues don't. And what that means is that if you look at the dynamics in the rotating frame, then the angle of rotation is phase independent. It doesn't depend on phi because the eigenvalues don't depend on phi. So this is great. It's a step in the right direction, but it's not enough because we want the overall dynamics of the sensor to be phase independent. And here, the final state still depends on phi because the rotation axis depends on phi. And the way that we would fix that problem is by adiabatically ramping the coupling between our sensor and the signal. So here, chi of t is some adiabatic ramp, which starts at 0, ramps up to 1, and then goes back down to 0. And by adiabatically ramping the signal, the state of the sensor adiabatically follows the rotation axis, which starts along z and ends along z. And as a consequence, the final state of the sensor is in fact phase independent. And this is exactly what we wanted. We wanted a phase rotation of the sensor, which didn't depend on the phase phi of the magnetic field. So that's great. This was all for a single frequency. or single state of the quantum computer, you can imagine. We ultimately want to do all of this in superposition, as I described. There's at the level of theory, it's very easy to accomplish this. You just take your control field omega 0 and you replace it by some field strength omega k, which depends on the state of the quantum computer. Again, this is sort of this is an easy replacement to make in theory. I will describe later how, like, what actual physical dynamics can be used to engineer this conditional phase response. Okay, and then finally, one final detail, the actual value of these rotation angles theta k, they correspond to the dynamical phase under the adiabatic evolution. So you'll recall from first or second year quantum mechanics, this dynamical phase, it's just the integral of the time-dependent eigenvalues, which to first order in B over delta is like B squared times T over delta. And the exact functional form of this dynamical phase is sort of not so important. The only important feature to note of this dynamical phase is that it is largest when k equals k star. So when you're in the marked bin is going to have the largest phase rotation. Why is that? Well, B squared T over delta k is largest when delta k is smallest. So that's when the spacing between your control field and your actual signal frequency is smallest, which corresponds to the frequency being in the marked bin. So that's sort of the only feature that we're going to need about these dynamical phases. They're largest when k equals k star. Okay, so that's the technical part. And then there's just one last element that we'll need to engineer the sensing oracle, which is some element of nonlinear signal processing. So to motivate this, let's again think about this idea of digitization and what's really the spirit of the digitization paradigm.
Richard,
Yes.
so is this a Berry phase or this is the other phase?
This is not a Berry phase, it's a dynamical phase.
It's the dynamical phase. Okay.
Yeah. Yeah, thanks for asking. Yeah, so this is just the integral of the time-dependent eigenvalues. Yeah. Good. So yeah, the last ingredient is this nonlinear signal processing. And let's remember, what digitization is or tells us to do. Digitization is the process of mapping a continuous phase response of the sensor, or actually, a linear response in B. So, as B varies, the response of the sensor varies linearly with it. We want to map that response to a discrete or really like nonlinear response of the sensor. And so the key question is, how can we engineer these nonlinear transformations in a quantum mechanical way? And the good news is that we don't need to invent a way of doing this from scratch. There is an existing algorithmic framework called quantum signal processing, which accomplishes exactly these nonlinear transformations. So I will just briefly tell you the relevant details for quantum signal processing, but there's a wealth of work on QSP. In quantum signal processing, there is some signal unitary, which is a rotation about some axis, for instance, the z-axis, by an unknown angle theta. And you repeat the signal unitary multiple times, and you interleave it with some control unitaries, which are optimized. So these angles, phi 0 up to phi L, they're angles that you, the experimentalist, get to choose, and they're about some orthogonal axis. And the resulting dynamics ends up being equivalent to just a z rotation about some angle f of theta, which is, f is in general some programmable nonlinear function. And so if you want to engineer a nonlinear response, then all you have to do is choose the right function f. And then for a particular choice of f, you compute the correct choice of control rotations, phi 0 up to phi L, and you run your QSP sequence. So what is the correct choice of f for us? Well, let's remember what we have. We have this elementary sensing unit, which is a controlled rotation of the sensor. And remember, the key feature of these angles theta k is that the largest of these angles is the angle of the marked bin. And what we want is also a controlled phase rotation, but it's by an angle which is discrete. So it's exactly pi, because we want a phase flip when k equals k star, and it's otherwise 0. And if we want to engineer this sort of discrete response, which amplifies large phase rotations and suppresses small phase rotations, then the right choice of f is actually a step function. So if we let f be a step function, well, that will amplify the phase rotation of the marked bin, amplify it up to an angle of pi, and suppress the phase rotation of all other states of the quantum computer, suppress them down to zero. And so you perform quantum signal processing using an approximation to the step function, and by interleaving the elementary sensing unit with these QSP sequence, then that engineers the sensing oracle and completes the construction. So that was basically all the details of the sensing oracle construction laid bare. So maybe now is a good time to pause for questions before we talk about some maybe like broader perspectives on our algorithm. If there are any questions about this technical aspect? Okay, good. I'll move on then. So, okay, I've just spent the past several minutes describing an arguably somewhat complicated protocol for detecting AC fields, which used a quantum computer and some entangling gates. And you might ask, rightfully so, like, was this all necessary? Did we really need to go to this effort of adding in a quantum computer? Is what you're doing really fundamentally different than what's possible in conventional quantum sensing settings? And that's the goal of this next section, is to really argue to you that our approach is qualitatively different, and that the enhancement in our approach comes from the use of quantum computation rather than collective enhancement or entangled resource states like it does in conventional quantum sensing. And in order to argue that, what we do is we prove very general lower bounds on classes of protocols which encompass existing or conventional quantum sensing approaches. And the first class of protocols that we prove a lower bound against is protocols which we call QFI based. So QFI is quantum Fisher information. Quantum Fisher information is sort of the standard measure of performance in quantum sensing. So the QFI, you can use the QFI to characterize the improvement that you get in moving from standard quantum limit to Heisenberg limit. It characterizes a lot of existing enhancements in quantum sensing. And so if you asked someone who is an expert in quantum sensing how you might design an AC sensing protocol, well, they might say that the best thing to do would be to distinguish perturbatively small field strengths from fields with strength d min just by maximizing the quantum Fisher information over the entire bandwidth. That would be sort of a reasonable guess at a good protocol for AC sensing. And our main result here is that, in fact, any protocol which works in this way, which maximizes QFI over the full bandwidth, must take a total time that scales like 1 over b min delta omega over b min. And remember that this scaling is the scaling that was accomplished by our simple conventional linear search protocol. And it is worse than the scaling that's achieved by our quantum search sensing algorithm. And so what we show is that this is really a fundamental limitation of any of these QFI-based protocols. And so the key takeaway here, first key takeaway at least, is that a non-perturbative approach is necessary to achieve the fundamental limit, this Grover-Heisenberg limit in AC sensing. And the second, maybe broader or moral perspective, is that this quantum Fisher information, which is typically the figure of merit that people use to characterize sensing performance, is in fact of limited use, at least for this AC sensing problem that we consider. Good. So that is one class of protocols that we prove a lower bound against. Another class of protocols that we consider is what we call classical signal processing protocols. And this is also a class of protocols which captures a lot of existing work in quantum sensing. These are protocols which are equivalent to applying some filter function to every sensor. So you can think of these protocols as just sort of classically controlling the exposure of a sensor to the external magnetic field. So these chi-IFT, they're like arbitrary functions, maybe satisfying some continuity property, but they're essentially arbitrary. So any protocol of this form, we call a classical signal processing protocol. And our second main result is that any such protocol also satisfies this same lower bound on sensing time. And the key takeaway here is that, in fact, a nonlinear approach is necessary to achieve this fundamental limit. And you can think of this as saying that sort of our use of digitization or our use of nonlinear signal processing is, in some sense, fundamental to the speedup that we achieve. Okay, good. So that was discussing the role of quantum computation in our protocol. We've talked about an algorithm. We've talked about its performance relative to existing work. But at the end of the day, there's sort of like one very important question, which is, can you actually do this in practice? Can you see these speedups in real near-term experiments? And our goal will be to answer this next. Okay, so to answer this question, let's look at what the actual requirements of any experimental protocol would be to run quantum search sensing. So first, we're going to need arbitrary rotations of our sensor qubits. The reason is that we do QSP, so we need to have rotations about the x-axis. We also will need global computational rotations, so global rotations of the computational qubits. And this is better than requiring single site control of the computational qubits. You just apply the same gate to all of your computational qubits simultaneously. So that's a weaker experimental requirement. And then finally, we'll need some way of coupling the computational qubits to the sensor qubit. And it'll turn out that Ising interactions between the sensor and the computational qubits are sufficient. Ising interactions are sort of the most prototypical interactions in nature. And so it's good that we can use such a simple form of interactions to perform our algorithm. So let me hone in a little bit more on why Ising interactions suffice. So let's consider this Hamiltonian, which describes Ising interactions between a single sensor, ZS, and a number of computational qubits, NQ computational qubits. So we have the Bayer splitting of the sensor and Ising interactions of strength Ji between the computational qubits and the sensor. And you can actually rewrite this Hamiltonian in the following way. So now instead of summing over states, instead of summing over the computational qubits, we're summing over the different states of the computational qubits. And this form of Hamiltonian is, in fact, it's exactly the form of the Hamiltonian which we needed to do sensing in superposition. So a controlled splitting of the sensor, conditional on the state of the quantum computer. So this is the Hamiltonian that we need in equations. In pictures, we get the following energy diagram. So if the state of the computational qubits is in the all zero state, then the splitting of the sensor is some value omega zero. Otherwise, the state of the computational qubits determines the conditional splitting of the sensor. And the marked state is now just whatever frequency is closest to the true frequency of the signal. So this shows that Ising interactions are enough to engineer this sensing in superposition. And this is sort of like the only interaction that we need between the sensors and the computational qubits. Okay. Those are the ingredients that you would need if you wanted to run the full version of our protocol. We also have a simpler proof of principle experiment, which we propose in our work, the goal of which is to demonstrate quantum computing enhanced sensing now or in the near future. And we do detailed numerical simulations of this protocol using realistic decoherence rates and coupling strengths. So we need to focus on a particular platform. We choose to focus on nitrogen-vacancy centers, which are a sort of a very well-demonstrated platform for quantum sensing. In nitrogen-vacancy centers, there's a 1 qubit, which corresponds to the NV electron spin, and that's used as a sensor. And the computational qubits, we're going to choose to be the long-lived C13 nuclear spins, which exist surrounding the NV center. And for our proof of principle experiment, we'll also focus on a slightly simpler problem. In the simpler problem, we assume that the field strength is known, and so is the phase. And the frequency of the signal is not continuously varying, but belongs to some discrete set. And in this setting, a lot of the apparatus in designing the sensing oracle, which was used to engineer robustness to variations in B and phi, that apparatus is no longer necessary because in this setting, in this simple discrete setting, the sensing oracle is just a 2 pi rotation of the sensor. So if we look back at the previous level diagram, all you need to do is apply a 2 pi rotation at the frequency omega k star, which corresponds to, in this setting where the possible values of the signal frequency are discrete. That's just a 2 pi rotation of the sensor. Okay, and I'll just sort of quickly flash some numerical results. The performance of our protocol, we quantified in terms of this improvement factor, which is the ratio of the conventional sensing time to the quantum computing enhanced sensing time. And here are some quick numerical results. And the key takeaway is that for realistic values of coherence times, coupling strengths, and sort of an as accurate as possible simulation of the existing quantum platforms, we can expect an improvement of around like 3 to 5 using these realistic parameters. And that's what's depicted on the left-hand side. And on the right-hand side, this is a sort of hopeful prognosis of the progress in these platforms. It shows the scaling of the improvement factor as the number of computational qubits increases. And this red dotted curve is a scaling that's like square root 2 to the n cube, which is sort of the improvement that you would expect from the Grover speedup. Okay, so that concludes the technical part of my talk. I'll now just briefly conclude with some discussion and outlook before we move on to questions. So what's next for quantum computing enhanced sensing, or maybe what are the most promising perspectives or directions? I think one very useful perspective on this work can be seen by thinking about the quantum oracle model. So the quantum oracle model is sort of, it's one of the only frameworks where we have, it's the only framework where we have provable speedups comparing classical computation to quantum computation. But in this oracle model, you assume that you're given as a black box some oracle, unitary oracle. And one perspective on our work is that we're sort of unlocking this black box by realizing such an oracle in terms of natural physical dynamics. So the perspective is that even though, like a common complaint about the oracle model is that these oracles are unphysical, where do they come from? One perspective of our work is that these oracles can be realized by natural time-dependent physical dynamics, which really occur in the real world. And this leads to a somewhat natural question, which is whether larger oracle speedups, so beyond quadratic speedups, can lead to greater metrological gain. There's some discussion and work on this in the paper, but I think it's a promising direction for the future as well. And then, one final future direction is in the design of error-corrected or logical quantum sensors. So in classical computation, our classical computers, they couple to external signals through many sensors. So video cameras, keyboards, these are all examples of sensors which couple the external world to our computational devices. And it's an active question of whether or not error-corrected sensing is possible in some settings. And in particular, maybe some of our digitization techniques can be used to beat conventional wisdom in error-corrected sensing and lead to logical quantum sensors in the future. Okay, that's all from me. Thank you all very much for your attention and interest, and I'd be happy to take any questions now.
So thank you very much, Richard. It was really very nice and very much pretty in time. So there's time for questions. If there's any, just press the raise your hand sign, and we will unmute you for questions. So go ahead. Okay. So there's some question in the chat. I think. No, I thought it was in the chat. No. Right. So then I have some questions. Yeah. So I really would like to have a global pictures. How is could you clarify better the workflow? I would like to see this. What is a full Grover step here?
Yes, good. So the you can view the algorithm sort of in layers in some sense.
Yeah.
The outermost layer is you run Grover's algorithm to find the bin which has the signal.
Yeah.
But to do that, you need to have a sensing oracle, which applies the correct, phase flip to the state of the quantum computer. The sensing oracle, 2 steps. The outermost layer is quantum signal processing, which does this nonlinear rectification of the rotation angle. And then the innermost layer is the sort of adiabatic Stark shift protocol, which performs this phase agnostic sensing.
Yeah, but usually in Grover algorithm, you need to. So where's the square root of the number of steps they're coming in? I mean,
it's the number of applications of the sensing oracle. So the sensing oracle takes some time to realize because you're sort of evolving under this external signal. So it takes some time. And then that sensing oracle needs to be applied square root n times. And so that's the square root n improvement.
So if you have a signal which is not monochromatic, you will find only one of them. I mean,
that's a good question. So whether or not it's possible to do some sort of Grover's algorithm, which is sensitive to multiple marked elements, I'll say that I think, we strongly believe that this is the case, that it's possible to have a non-monochromatic signal. That's something we're actively working on. I think with some guarantees on perhaps like the minimum spacing between, if you have if you have many sort of almost resonant tones in your non-monochromatic signal, then that's sort of equivalent to a larger coupling strength. So you have some like minimum, you have some guarantee on the spectral density of your signal. So that's sort of some spacing between the different tones. In that setting, we strongly believe that it should be possible to.
I see.
But there's some technical aspects which will.
And moreover, in this entity center, so you're saying you're using your qubits, your computational qubits are the nuclear spins?
Yes.
So you have really computational control on that, as you can do gates with that.
So there are a number of experimental groups which have which can perform, in fact, like algorithms and entangling between an NV center and nearby nuclear spins. They have like resolved single site control of nuclear spins. They can use Ising interactions to engineer entangling gates. Like these things demonstrate in many platforms.
So, but what's the number of these computational qubits you can reasonably think of? I mean, is this a high number or?
Yeah, I think there are like existing experimental works which have characterized upwards of 50 nuclear spins in the vicinity of a single NV. Now, it might not be possible to have the level of control that you might want on all of these. I think a reasonable number is around 8 to 12. And so our predicted improvement is for, 8 to 12 new by new.
Because the Ising couplings will be,
they're refrigerated and exactly. And,
so you don't need them to be equal, no? These Ising couplings.
Yeah, and in fact, having some variation in these Ising couplings is good because that leads to a wider spread in these conditional splittings, which allows you to probe a larger bandwidth. So it's in fact good to have some random variation in these couplings.
Cool. Yeah. So a last question: this K basis is the computational basis in this. Okay. It was.
So K ranges from 1
to the
n, 2 to the n, where n is the number of abitic qubits.
Of pins. Excellent. So
there is one question in the Q&A, Jordi.
In the Q&A answer. So let me thank you for your very clear presentation. For some reason, I have a question. Are there known protocols that do not use quantum processing that do not belong to the two types of protocols for which you develop lower bounds?
Yeah, I mean, this is a great question. I would say that, yeah, so like, yes, you can imagine quantum sensing protocols which don't use a quantum computer but which don't, which are sort of have some aspect of nonlinearity to them. So let me first say, like, for any existing quantum sensing protocol which doesn't fit into these two types, you can sort of by hand show that they're not capable of achieving our result. But we would like to prove maybe a more general theorem which rolls out some of these protocols as well. I think in particular, understanding what is possible using very small quantum computers. So if you have a limit on the number of, for instance, like if you had just one sensor and order 1 computational qubits, showing that this, understanding the performance of a protocol which has these resources is, I think, a great open question. I mean, and the answer would be interesting either way. Either these protocols it's not possible to use them to achieve what we achieve, in which case that's stronger evidence that quantum computing is a useful resource in sensing. On the other hand, if you actually could design a much better protocol for AC sensing using these resources, then that would be a boon to experimental progress. Because again, this is a real problem that people are like, wow. So, yeah. Mm-hmm. I hope that was a clear response.
Yeah. Any final questions? So I have a curiosity. I mean, this nonlinear step function that you achieve, no, it really brings to my mind the neuron response. No, this non. I don't know if you have thought about this. I mean, which in quantum is difficult because quantum is linear, and have you thought about the possibility to implement this in? I mean, this nonlinearity of classical neural networks within using these protocols to have this.
Yeah, it's a great question. Yeah. So I'll say, like, this step function that we use. I mean, we were not the first to use signal processing to engineer this sort of response. There's a huge wealth of work on quantum signal processing, some of which is comparative with sort of quantum convolutional neural networks or these other quantum versions of various machine learning protocols. I'll say that, like, yes, there is certainly some connection, and understanding other application areas for QSP is, I think, QSP has a lot. I mean, at this point, like, a very exciting track record. It has achieved.
Okay, maybe it has to be
understanding understanding if they are useful for QML is.
Yeah, exactly. Okay, so thank you very much, Richard. It was really, really enlightening and very, very pedagogic, and we really thank you for this nice talk. And we reconvene in 2 weeks, so please, everybody, stay tuned, and we will be back soon with more interesting seminars. Thank you. Thanks all for being there, and thanks, Richard.
Yep. Thank you again for the invitation.
Goodbye.
Thank you.